We have Ag plus 1 electron yielding Ag solid. So how long does it take, how long does the current have to flow to obtain this deposit? So we want a time, and how many units does time have? 1. So we'll start with seconds over here. This is 1 electron per 1 mole of silver ions. This is 1 coulomb per 1 second. This is 1.54 grams. Out of these things, which one makes sense for us to use? Yeah, right, 1 unit. So we start with 1.54 grams. Then we need to change from grams to moles, 107.87 is 1 mole. And then using this equation up here, we know that every 1 mole of silver is 1 electron. Now, if we turn back here, the number of coulombs per mole of electrons is this 96,485. And right there, that is on the data sheet. That's the one that you're going to have to, I mean, even though it's on the data sheet, that's the one you're probably going to have to make the stretch on, remembering like, oh, I need to go from, I need to get to coulombs so that I can use the amps. Every 1 coulomb takes 1 second. Let me multiply that through. I was like almost here, and then I looked down and I realized I didn't have my watch. I'm like, it was almost worth calling the day off. I sit here and press buttons all day. What am I, an astronaut? 46485. And we get 1,377 seconds. If you wanted to, you could convert this to minutes or whatever. 3 significant digits for me, so I'm going to go with 1370. It's 1377 is going to be 1380. What way? Let's see. What weight of chromium would be deposited in a second cell containing 1 molar? And having an anode of a platinum cathode by the same current in the same amount of time used in a silver cell. Are we going to just grab this time and do what? Yeah. 1380 seconds. And we want, I'm using that because it's the same amount of time. I want to find the weight of chromium. So I'm going to put grams chromium there. So we need to change the seconds to what? Coulombs. Every 1 second is 1 coulomb. And every 96,485 coulombs is 1 mole of electricity. Problem here is we have chromium. The difference here is we have chromium. What does that mean? Yeah, it's chromium 3 nitrate, right? So that means we have Cr3 plus. How many electrons do we need for that? 3. That will give us Cr solid. So that means that here, for every 1 mole of chromium, we actually need what? 3 moles of the electrons. And then every 1 mole of chromium is 52. So 1380 times 1 divided by 1 divided by 96485 divided by 3 times 52. We get 2.48, or I'm sorry, 0.248. This times 10 to the negative first. What do we think there? If both electrodes were platinum in this second cell, so we're not depositing any more of the chromium here. Both are platinum in this second cell. What volume of O2 gas measured at standard temperature and pressure would be released at the anode while the chromium is being deposited on the platinum? All right. Let's take a look at this real quick. So that is a hydrolysis of water, basically. I gotta stop sharing, right? So let's take a look. Here's our guy, and you guys are more than welcome to get around somewhere you can see this. My battery from last time. Cell battery. See if you got any charge. What I'm going to do is, you can see I've got both of these. This isn't platinum because this would be way more expensive if it was, but we've got 2 electrodes. Notice we don't have any cadmium in this solution, so we're not actually plating something with cadmium, which means if our oxygen is, but since we're putting electricity in there, basically what we're going to do is we're going to form O2 and H2, since this is a electrolytic cell. You got any energy in this battery? Battery's dead. Let's try another battery. You guys have any batteries? You need tested? Battery's dead. Here, so you put your tongue on both sides of that and see if it gives you a zap. What's that? I don't know, maybe you got one of those freakishly large tongues or something. You just got a normal little tiny small tongue. Didn't I have a 9-volt in here last time? Didn't we use that for something? Yeah. Could hook it up to this, but I don't think I want to do that. I don't think it's worth it. Why? We can do it the old-fashioned way. Here I have a generator. Since I cannot find the battery, let's try a generator. They use these in physics. What? You guys use these power sources. So, as I generate electricity with this, You can see bubbles forming. That kind of sucks. That's no fun. Let's just hook up a power supply to it. Just have to be very careful I don't blow the power supply. What's that? It'll shut off before I blow it. This kind of stinks. It looks like somebody grabbed my other wire. Man, somebody just doesn't want you guys to see the electrolysis of this today, huh? That's insane. Why would somebody grab that? Grab only one wire. Kids. And somebody actually took that, put it into their pocket or book bag? That doesn't seem logical, does it? Ah. Last place you look. There we go. So I don't know if you guys can see that, how that's gotten cloudier over here, but you should be able to see maybe at the top, the very top up there. I don't know. Can I even like change the way that this one works? Hey, very little. Oh, wow. Didn't change on that one, does it? Oh, this is the other one, yeah. It should work. It's weird. Let's try that. Get it off of you. Is that what you said? You're wearing a mask. Nobody can identify you. This is Dylan. But as we let this go more and more, you should be able to see that we have a volume up here. So on the electrode, the actual gases themselves, we're getting the hydrogen and the oxygen from H2O to basically undergo, and there's a little bit of a salt in here, sodium hydroxide, to undergo the process of electrolysis. And which one do you think is the hydrogen? This one or this one? Your last, right? This one right here would be the hydrogen. How did he know that? You didn't guess. How'd you know it, Dylan? You did guess?
It just made sense in my head. Hydrogen is weird.
There's more of it.
Yeah, that's what I was saying.
The ratio should be 2 to 1 H2O, right?
Yeah, that's what I said.
Oh, good. So that is electrolysis. And we can form the gases this way. So what we're going to see over here is, or on this problem, I should say, actually, I probably should, otherwise that battery will be dead. That's what they're asking. They're asking us for the production of oxygen on the platinum. So let's take a look at that. Oh, man, that's grainy. All right, so we know how much chromium has been deposited, right? So that's what it's saying at the anode while the chromium is being deposited at the cathode. So it's the same current and time. So we could start with the time and just go with the oxygen. The thing is we need to figure out the formula for this. So if we come up here, we've got right here 2H2O, 2H2O yields O2 plus 4H plus. If we take a look, how many electrons is that going to be per mole of O2? For every 1 mole of O2, it takes 4 moles of the electrons. So what do you want to do? Do you want to do the seconds or do you want to do the chromium? I'd say we just go ahead and do the chromium. Grams of chromium, because we've already got a lot of this set up, don't we? And every 52.00 grams of chromium is 1 mole of chromium. And for every 1 mole of chromium, we get 3 moles of electrons. And since we're at moles of electrons here, we can now go directly from moles of electrons from the chromium to moles of electrons from the O2. They do say that this is at standard temperature and pressure. So unless you want to sit there and do a whole nother problem with P equals nRT, you have to remember what? 22.4. Every 1 mole of any gas at STP takes up 22.4 liters of space. 0.248 divided by 52 times 3 divided by 4 times 22.4. That gives us 0.08, 0.248, 52 times 3 divided by 4. All right, gives us 0.0801 liters. Questions there? All right. 3 significant digits, 3 significant digits. Cool, cool. Let's take a quick look just to make sure that you guys get this diagram, this idea. Share this with you. So here's something similar as to what was happening in that. Like you had the depositing, in this case, instead of chromium, I'm sorry, instead of copper, it would be chromium. And then you would have on here, those oxygen bubbles coming off and O2 gas being released. Instead of using, they didn't actually tell us what they used there. We just assume that it's aqueous or whatnot, or in this case, we've got the sulfate and the OH negative. Yeah, there it is, aqueous. So H plus and OH negative. And then we give this oxygen the electrons to basically, it's going to pull those electrons and then form on the anode. Boom, boom. The other big part of this chapter is the delta S, delta G, and delta H. So if we take a look here, sharing the wrong thing, thank you. One day off Zoom and I forgot how to use it. All right, make it bigger for you guys. This one's pretty weird right here. If we take a look, what did they give us here? They didn't even say anything about it. What are those potentials? What are we used to on the table? We used to be given the reduction potentials. What are these? Yeah, that's pretty cheap. These are oxidation potentials. That means we'll have to change them. But what is being reduced up here? Reduced, going down, right? So here we have 0 and here we have -1. So that means that bromine is being reduced. And what does that mean? Iron is being oxidized from 2+ to 3+, that's oxidized. So if we look at our formula, if we wanted to find the E potential, which we're going to need for later, standard potential, we would need to basically take the reduced plus the oxidized or whatnot. So if we want to do that, we need to switch this to be what? Instead of 1.07, or I'm sorry, -1.07, it becomes, yeah, right? So we're going to switch this to be reduced. .07. With that, we can take 1.07 and we're going to add to that the oxidation potential. So it'd be 0.3 something. We'll get to that later. So let's take a look here. Determine delta S. So they give us our standard entropy potentials. If you recall, delta S equals the summation of the products minus the summation of the reactants. What else do we have to do? We have to multiply it by the what? Right. So notice that this is in calories per mole. So we may have to change that into joules or kilojoules in the future. So there's 1972, they were playing a bunch of weird, like let's give them the oxidation potentials instead of the reduction potentials. Let's give them calories instead of kilojoules. So that is a little bit weird. So let's do this. We have 2 times the BR2. We're going to add that to 2 times the Fe3 plus, because we have 2 there. These are our products. And then we're going to do the reactants. Subtract 58.6 and oh, I didn't do the number here. I'm gonna go ahead and do the number there real quick. I actually wrote the BR. So 2 times 19.6. And then 58.6 here, and then we've got 2 times the Fe2 plus. So plus 2 times 27, negative 27.1. $2.19.6 plus 2 times negative 70.1. I got negative 1.01 times 10 to the second, or negative 101. Gonna subtract from that 58.6 plus 2 times negative 27.1. We get 44. So 101 minus 44. Oh, I'm sorry, it's not 44. 4.4. So 101 minus 4.4, that's going to be 105.5, right? And notice this is what, though? This is in calories per mole Kelvin, or actually mole degree Celsius. Calories per mole degree Celsius is the same as calories per mole Kelvin. Why? That's a change, right? Maybe not in this case. We'll leave it at this. Hopefully we don't have to change it. If we do, maybe we will. I don't know. So there is A. They didn't give us any type of stipulations on that. So next, if we take a look, B, determine delta G. So if we take a look, delta G equals negative NF E naught, where this is the number of moles of electrons. This is that Faraday's constant. And this is that cell potential that we're going to need to calculate again. So we have 1.07. And we're going to add to that. That's the reduction potential. We're going to add to that negative 0.77. There we go. It gives us 0.3 for E. F, Faraday's constant at 96,485. That's coulombs per mole of
Can you
electron.
move the paper up so we can see?
Yep.
Thank you.
And we've got to do our negative N. So we got to figure out how many electrons are being changed each time. So we can choose to do that with either of the half reactions up here. So if we have Fe2 plus going to 2Fe3 plus, how many total electrons are being moved? 2, right? 2 electrons being moved. And we could do that also with the Br2 going to the 2Br negative, 2 electrons being moved as well. So that's going to make our N a factor, multiplying this by a factor of 2. The voltage is actually positive. So we know that this delta G should be what? Delta G says is spontaneous if delta G is negative. And we know that we have positive voltage here. So that means that delta G should be negative because this is a spontaneous reaction. So negative 2 times 96,485 times 0.3. And we get negative 5789. And this is actually going to be joules per mole. Oh, 1, 2, 3, 4. Boom, boom. Questions there? Yes. This is a time sign.
No, like just those points. Like,
That's if we change both of these to reduction potentials. That's a good point. I skipped right over it. So in reality, you can take the reduced reduction potential plus the oxidized oxidation potential. What we've been doing is and this is something that you're going to have to get fixed in your mind because there's so many different ways you can think about it. You got to choose one. This didn't allow you to do that because they gave us oxidation potential. We've been using the formula this, E naught cell equals the reduced reduction potential minus the oxidation reduction potential. So since both of these are oxidation potentials, we change this to the reduced potential by switching the sign. To make this one work, we would also have to change this to the reduction potential. Does that make sense? You got to be in the same type of potential for this. The reason this is easier in my mind is because most of the time you're given the reduction potentials, right? That apparently is something that in 1972 they were like, let's not do that. Let's not give them that. Other questions? All right, let's take a look at C then. Let's take a look here. 105.5. I'm not liking this, but if we take a look, delta G equals delta H minus T delta S. We should be able to rearrange this formula to solve for delta H. If we rearrange this, I'm going to flip the formula, and basically delta H is going to be equal to subtract delta G from both sides, right? Negative G, negative delta G, plus, actually, no, let's do it that way. That's a lot easier. Let's add T delta S to both sides. There we go. So I'm going to go ahead and put it down here, plus T delta S, plus T delta S. So we get delta G plus T delta S. We got our delta G up here. It is negative 57,891 joules per mole. And we're going to add to that. And here's the thing I'm wondering, that's per degree Celsius. So the temperature let's do that. If we keep the temperature, what is standard temperature? Oh, yeah, we want 298, right? I think we're going to have to change this from calories to joules and from degrees Celsius to 298. But it would be per degree Celsius. And 1 degree Celsius is how many degrees Kelvin? 1. Does that make sense? So we can flat out change that to, for every 1 degree Celsius, it's 1 degree Kelvin. Even though we don't like degrees Kelvin. We can't keep this as calories though. What do we need to do to that? We need to change it to joules. So let's do that right here. I'm just going to go ahead and say that's per mole Kelvin as well now. I don't want to have to deal with that anymore. Every 1 calorie is what? 4.184 joules. So that gives me plus 298 times 441.4 joules per mole Kelvin. We're happy with that? So we're going to then take that and multiply it by 298. Yes. This is not negative, is it? Oh, yeah, you're right. Thank you. There we go. Negative 441, right? It's negative 101 minus 4. Yep, I just didn't carry it down there. Thank you so much. And then if we take a look, 298 times that, we will negative that answer. And then we will add it to negative 57,891. And we will get negative 1, 2, 3, 4, 5. And if we wanted to, we could change this instead of joules per mole. We could change it to what? Kilojoules per mole. So it'd be 189.4 kilojoules per mole. But let me ask you this, delta H being negative, does this make sense for spontaneous reaction? Yes, right? Delta G being negative, does that make sense for spontaneous reaction? Yes. Entropy being negative, change in entropy being negative? No, that's more order. But at this, low of a temperature or whatnot, that's okay. And this being high enough negative, it being enough exothermic, that's okay. I'm sorry, this being this means that the delta H is going to be hugely negative. So we're still good. We got the thermodynamic requirements for all of that to be spontaneous. We're good. I think that's all I got for today. And that's surely enough to get the FRQ done. Maybe we'll take a look at some of these other problems as we review. There is a huge amount of multiple choice on the back for practice. And that's pretty much it. You've almost completed AP Chemistry. Questions from the home team? No? All right. Have a good day, guys.